Hi, I am Kunal, and I have done my master's from in physics from IIT Bombay, and I've also done my BSc in physics honors from Hansraj College, Delhi University, and today I'm will be talking about center of mass. It's a very fascinating topic to me, and not just to me. It's a very fascinating topic in nature, and let's just start from it. So one of the question before starting is why to study this center of mass? Why did we come up with something like that? So if I say you that Newton's law that you studied, I'm sure you must have studied something like this, that if you have a point mass object that is mass m and you apply a force to it F, then the acceleration multiplied by the mass is equals to force. This is Newton's second law. This is given by Newton. Now, in the Newton's theory, this formula is applied only to a point object. But in our daily lives, we don't have point objects. For example, a ball, a human being, a car, a airplane, a jet, or anything that we see is not just one particle. But these are like objects made up of a large number of particles. Now, how to apply Newton's law? Now, in order to understand the motion of that object, we have to apply force is equals to mass into acceleration to each and every point on that object. For example, if I have a ball and then at each and every point, if I keep on applying and then try to study the acceleration of each and every point on that ball, and then try to make sense of what will be the net motion on the ball, that is quite complicated. Maybe before this topic, you must have read these. You must have done these numericals in which you are applying F is equals to ma to a ball. But that is not correct because according to the theory, the Newton's laws are applied to point mass objects. And the objects that I'm talking about in daily lives and all that, these are known as extended objects. It's nothing just a name given. Extended means it's made up of large number of particles, for example, ball and all. Now to apply F is equals to ma and to study the motion of these extended objects, we need to come up with some clever idea. And that clever idea is center of mass. Now, what is that? That is the amazing part. Now, for example, I have a ball. Now, instead of tracking the motion of each and every particle, I'll just imaginary, I, I'll just imagine there is one point on the ball, some point there is some point on the ball, in the center of the ball. I replace this whole ball by that one point, and I'm assume that the whole mass of the ball is concentrated on that single point. And whatever force that I was exerting on the ball, the external force, a 10 Newton, 20 Newtons, whatever, is now being applied on that center point. Now, the interesting part is that whatever acceleration that my ball will have will be equal to the acceleration that the center of mass point, this particular point that I'm calling center of mass, will be having. So why not talk about this particular point and just forget the entire ball? But can we do it? So what I am saying is that this that the Newton's second law is applied like this. And once I have acceleration due to this acceleration of this center of mass, I can say I have acceleration for this point mass for this whole ball. But can we do this? The physics says yes, and I'm going to prove it. Or I may not, depends on the time. But anyways, but I have to emphasize, let's go again over all over again, that I have a ball or I have a, for example, car. Now to calculate the motion of the each and every power point on the car, that is very hard. But what I can do is to imagine there is a point at the center of the car where the mass is somewhat balanced, and imagine at that point the whole mass is concentrated, and the external force that I've applied on the car is now applied on that mass and track that particular point, and that is my center of mass point. Enough with the definition. Let's come up with some try to come up with some so this is the definition that we had, that we defined that if you apply an external force on that center of mass, and get the acceleration, then that acceleration is equals to the acceleration of the body. So in a way, I can calculate the acceleration of the body through the acceleration of the center of mass. So this is a clever trick that they played with us. Now, let me come up with some other example where center of mass is very useful. Now, for example, you're spinning a ball and throwing a ball to a friend. For example, you're throwing a ball to a friend by spinning it as well. So when you track the motion of the ball is also going a projectile like this, but it is also spinning in its path. So let's track the motion of the, for example, there is a boy here named Rahul, a very common name. Let me just say Om. And there is a boy, let me be religious today and say there is a boy named Krishna. Now these two are playing with a ball because they are my students and they want to analyze projectile motion maybe, and they threw and Om threw a ball and it reached Krishna, but Om also give it a little twist to the ball so that the ball is not just doing this projectile motion. In actually the ball motion is something like this and also moving forward. So ball consists of two motions. One is the projectile motion and spinning motion. Now it's very hard to analyze the motion of the ball. Now what will happen that once I imagine that the ball consists of only a single point and I track only that point, now that point, that center of mass point, will be able to track the translatory motion, but won't be able to calculate this spinning motion. So that is where we have to remember that is a limitation. We can't track the spinning motion of this by doing this particular analysis. Now, spinning ball and rotating cylinder, just the example that I gave you, that is all for that. Now, another topic. Now, another question is that can we just find the center of mass for any object just by guessing? Like it is at the center of the ball, or is it some certain point? No, there is actually a method to do that, and I'm coming on that only. So let us take things very simply and just take a very simplistic case where we are saying that there is a system, there is a two particle system. I am considering a very simplistic system that is a two particle system in one dimension. That's how physics works. Do the simplistic case, work on the complicated ones later on. So for example, it's a body consisting of two particles, two point mass particles on one particular axis. This is of mass m1, this is of mass m2, and they are lying on the same line. And I'm calling this line to be x-axis and this point to be the origin. I can choose my origin. I have choice to choose my origin. Basically, I can also choose at the center, but just I'm choosing it here. Now, the distance of this particular point is x1. Okay, the distance of this m1 point is x1 and the distance of this m2 point is x2. Now what I say that the location of the center of mass, where will be the center of mass will be located, depends upon the average position of these two masses weighted by their mass, the average position of two masses. So if I say that both masses are equal, you may have a certain idea that it's lying somewhere on the center. But if some mass is greater, for example, m2 mass is greater, it is lying towards more here, the center of mass position. So the formula for that is given as m1 x1 plus m2 x2 upon x1 plus, sorry, m1 plus m2. So if m1 and m2, you can take a special case where m1 and m2 is equals to 0, then you will get x for center of mass as x1 plus x2 by 2, which means it is lying indeed at the center. Now, if m2 is greater than m1, if m2 is greater than m1, then it lies somewhere here. Now I have certain idea of where it to look at. Now, just continuing this particular way of calculating the center of mass location, let me extend to more than one dimension. Let us make it a bit complicated. Now, suppose I have these two particles. 1 second. Yeah, everything is fine. Everything looks fine. So for example, I have a two particle system only, but now it is not just in one axis, it is in three-dimensional axis. So this is M1 particle, which has coordinates x1, y1, z1. And this is another particle M2, which has coordinates x2, y2, z2. And this is the frame, this is the origin, and so on and so forth. Now, this is extending to infinity, like if I draw it. So one particle is here, another particle is here, another particle is here. Now I want to find out where is the location of the center of mass. So just translating the idea which how we did in the previous case, the for this case the center of mass will be like this. Just the same formula. And for the another dimension, I can also write just replace x by, sorry for the, now in this case it's lying with the line connecting between these two at the center or somewhere in at this line it will lie. Okay, makes sense, somewhere at this line. Now anyways, and similarly for z you can write the same formula. Now instead of talking, you must have also studied vectors. In vectors, how would we write it? The location of the center of mass. So for the vector, the location of center of mass is given as x center of mass I cap plus y center of mass j cap plus z center of mass k cap. And it looks like when you put down the entire values, it will come out to be summation, oh sorry, mi r1 plus m2 r2 upon m1 plus m2, where r1 and r2 are these 2 points, the position vectors for these two mass objects. This is a very important formula. And let us write down this formula very clearly here, that the position of the center of mass. So let me draw the diagram again. For example, if you have these two mass objects, and this is the frame of reference, this is the origin, this is R1, and this is R2, the position vector for the second mass particle. Now what will happen? The center of mass will lie somewhere here at the line connecting or wherever. This is just an intuition, but you have a formula to calculate it, that it is M1 R1 plus M2 R2 upon M1 plus M2. We'll be doing a question about it, then it makes simpler. So this is for only a two particle system. Let's introduce n number of particles, because body doesn't, a general body does not contain only two particles. It contains a large number of particles, n particles, for example. Now let's take a case where I'm taking n number of particles. So 1, 2, 3, 4, 5, 6, 7, 8. So there are like a large number of particles, 1,000, 2,000 in Avogadro number. You understand? In a gas, the Avogadro number, 1 mole of gas contains Avogadro number. So it's like 10 to the power 23. So it's large number of particles. Now for that, if I calculate the center of mass position, I just have to, not just R1 and R2, I have to include M3, R3, M4, R4, M5, R5. And just by continuation, I can write. If anyone has doubt, he can ask me how we are getting this. Basically, summation Mi. So what I'm doing, I'm adding the masses and all that, M3R3, and this is what I'll get. This is very important for your formula solving, but this form where we are calculating the individual coordinates, that is also important in which for questions, which we will see. So just to apply these concepts, किसी को दिक्कत नहीं है? Does anyone have any problem with this with this formula? This one looks little bit complicated, I agree, but it's actually will be like if you try to understand that the coordinates can be easily found out like this, and for n particles you can increase it to like m3x3 m4x4, and then the same way it is like it is written in the vector form. Now, depending upon the question, which formula to use, it will be very clear. Now, let's try to do a question. And this is the question in front of you. What does it say? Find the center of mass of three particles at the vertices of an equilateral triangle. The masses are like this. Each side of equilateral triangle is 0.5 meter long. So I won't be doing the entire question by my hand. I'll just give you an idea about it. It's a very easy question because for hard questions we can do together. So there are three mass objects, point mass objects. It's a three particle system. There are three and they are unequal masses. They are not equal. And we are asked to find out the location of the center of mass. So basically, they are asking us to find XCM, YCM, ZCM. For that, I must know for all the three particles what is the X and Y coordinates. So for a particle, so this is will be like MA, XA plus MB, XB plus MC, XC, and MA plus MB plus MC. See, it's a very simplistic question. And you know the masses, it's given 100, 150, 200. And in the, and you also know the XA, XB, XC here, it's given very, this is XA, this is X coordinate, this is X. Okay, sorry, what is A? You can just take this to be A, this to be B, and this is C, for example. And the same way you can, this is X, this is X, and here it is 0, 0. So this is XC. And similarly, you can find out. It's a very easy question. I don't think so. We should like spend much time on this. You will find that you'll get the coordinates of center of mass. Now I want you to intuitively think about it. Where will be the center of mass? Now, for example, all masses would be same. What would have happened? So let's take an example of a ball. Where is the center of mass of a ball? You must have got an idea. The center of mass is that particular point where we can imagine that there's a whole concentrated mass, an intuitive way to understand it. So a ball, it is at the center of the ball. But for a triangle, what is the geometrical center of a triangle? It is the centroid, right? So a geometrical center is the centroid. So this, if all the masses are equal, the equal contribution comes from all the three sides and it forms at the center. So the centroid of the triangle becomes the center of mass. But if in this case, for example, the masses are unequal, so towards the higher mass, so it will shift more towards the 200-gram mass and towards this side. Now, this is somewhere like, I guess this is somewhere where the centroid is. Centroid is somewhere here or what? And now this is the answer. See in the figure. Sorry, I've given the answer ultimately. But okay, so Z center of mass will be 0 because it's not given. Anyways, so this is the centroid of the triangle, geometrical center. हमें पता है, लेकिन it is shifted like this. So it is towards up side and towards here because the masses are here higher than this 100-gram. So it shifted towards that. So just an intuitive way to understand numerical. And now how much time do we have? So, how much time? Just a second. Mm, I don't know how much time we have, but let's do it. So let's do one more topic, that is conservation of momentum of center of mass. Now I said that the position of center of mass is given by m1r1 plus m2r2 plus and so on, right? mnrn, right? And here it is the total mass of the body, right? Now, for example, I take this m here and I can write it like this. Now, for example, differentiate with respect to time. Now, what will happen when you differentiate? Mass will come out. This R will be differentiated, it will become velocity of center of mass, right? MV, CM, M. And here also I'm differentiating on the both sides, on both sides. Here will be the velocity of second particle, and here's the velocity of nth particle. Now this looks like the momentum of center of mass into velocity of center of mass, and this is momentum of first object, second object, nth object. Now taking the momentum of all the objects is essentially the momentum of the whole body. So I can say this is a momentum of the body, and this is the most momentum of the center of mass. For example, the body is the ball, and the center of mass is that point. So this is position momentum of center of mass. This is momentum of entire body for the by the whole body, like the whole all the particles. Now this is we know. Now according to Newton's law, we know that F external, whatever we applied, will be equal to dpcm by dt, isn't it? This is rate of change of momentum of center of mass. And now if external force is zero, so if we have a system where I'm not applying any force, for example, a ball, then the rate of change of center of momentum is zero and momentum is constant or conserved, does not change. Now that is a very useful result. We will be doing numericals about it, and I've not included the numericals, but there is an example that I can talk about in this case. In this case, the example that we have to understand this, for example, there is a bomb that, for example, let's make the situations really tense. There is a building, and here is a terrorist, and he took a bomb here and he threw the bomb to this building. He's just doing practice. Let's not take any real life cases. So he threw a bomb on a building. So the bomb went like this. But what happened? This terrorist was not very skilled one. So he didn't time it properly and he plugged the bomb earlier. So the bomb didn't fall on the building and didn't blast. It blasted early. So the pieces went like this. Some went ahead, some went on this, some went on this, and some like this. Now, what we say now, if we would have timed it properly, the bomb would have went very nicely like this, a projectile motion. Suppose if there is no building. But what happened is that he didn't time it properly, and the pieces went like this. There are a lot of pieces. For example, it went three pieces went like this. Now, in this particular example, there was no external force. Now, because there was no external force, the conservation of momentum of center of mass holds. That the center of mass का momentum is conserved. So initially, मान लो, initially in the center of the ball, this was the center of mass that the ball was throwing. He was throwing, and it was following a trajectory. And the center of mass must have been following this particular trajectory. If the bomb would have not blasted and all. But what happened? It blasted in between, and the bomb blast because of the internal forces, not any external forces. Internal chemical energy वो करके it blasted in different directions. Now, because there was no external force, the conservation of momentum will be still holding. And so the now if I calculate the net now after the bomb blasted into three pieces, and I can this is mass m1, mass m2, and mass m3, and I calculate the location of the center of mass after the collision, and I track the motion, it will come out to be the same as this. And that is known as conservation of momentum of center of mass. It's a very fascinating topic, and there are a lot of numericals that are asked in your JEE and NEET and other exams. It's a very interesting topic. Now, let's just end our session by doing some takeaways. What did we look at? We looked at the definition of center of mass. First of all, we looked at the need of center of mass. And then we looked at the definition of the center of mass, and then we looked how to locate center or location of center of mass. We did for first two particle system, then for many particle systems, n number of particles, came up with a formula like RCM is equals to summation mi ri upon summation mi. This is the location, and we also come at the fifth point was F external was mass into acceleration, dp cm by dt. So this was all. And thank you for the lecture. If you have any doubts, we can take care of them.